Oh, we're okay now, are we? Cool, thanks. Good to know we're all right. So Tex is going to give his final talk, and having told us about stretching the meaning of OPV, we're now going to move to Star Trekian theme, which is next generation OPV. So Tex.
Okay, thank you. Okay, so this is a short communication on work that has been done, I think, in the last 2 years. I think we started in April 2 years ago, right? When Sean and I were teaching at a conference in Philadelphia. Right? Yeah. And we started thinking about, you know, let's do some theory and thinking about solar cells. How good, what would be ways to really improve OPV? You know, what could we really do in order to make a next step? How could we optimize in a different way? And so Sean and I started thinking about it. It was great fun, but you know, you're about 3,000–4,000 miles apart, so things don't go too fast. Although there's internet, but maybe we're a little bit old. And but then at home in my university, there's also Jan Anton Koster. You have heard that name before because he has these drift diffusion models that he uses to do a lot of modeling, and there's quite some publications with results from him. He developed that in the group of Paul Blom, but I always say it's Jan Anton's thing. Okay. So anyway, Jan Anton and I also started working together, and then it became a nice trio work, and Sean visited us a few times, and we had great fun in the last 2 years. And just a little while ago, we had the publication of our fruit, and this is what I'm going to talk about. And those are the pathways to a new efficiency regime for organic solar cells, meaning, I hope you understand that we mean a better regime, right? Good. So, because, you know, it's really amazing. There's, if you are in these conferences with the people, especially with the OPV people, there is what I call something like a Calimero effect. You know, most people that work with OPV are in one way or another indoctrinated. They're full of the idea that OPV will never be as good as inorganic. There is something, you know, it's, I don't know, but it's in there. You know, people are really willing to believe that we could never have more than 12%, for example, for simple benefit. You can find it in the literature. Yeah. So there is you have the good inorganic solid-state solar cells, and you have the crappy ones with the molecules. And I put something else here, by the way, which I hope can also inspire people. I'm not going to do it, because I simply am not good at inorganic molecular chemistry. But there are some people still, not too many in the world, that do molecular inorganic chemistry. You can have inorganic molecules. Most people even don't know that they are. Yeah? For example, you know, everybody knows a benzene ring, C6H6. But you can replace the carbon atoms by nitrogen and phosphor atoms. That's NP, NP, NP. And you have an aromatic ring without hydrogen atoms, but it's an aromatic, it's a benzene kind of ring, but now made with nitrogen and phosphor. That's an inorganic molecule. You see my point? And of course that has delocalization, and has pi conjugation, and you have a whole show. Yeah? So there is much more to do with molecules than everybody in the world is doing. There are many more possibilities, and I'm not going to discuss them. But I just want to say that inorganic molecular solar cells would, in principle, be a field. But what we want to do is we say, okay, here is this big barrier. And is this real big barrier, is it real? That's the point. Okay, so the next thing is, of course, to tease everybody in the audience that's working on inorganic materials and say, there's only two interesting fields, the best ones and the crappy ones. And let's go for the crappy ones, because here's where the action is. And what we want to do is, and we're not the only ones, we say, okay, here's where we came from, here's actually where we came from, but it doesn't matter, or here's where we really came from, of course, tiny cell, Kodak cell here. But anyway, here's where we draw the line because it's more optimistic. And we go through the present point, and we just make a linear, and we reach 20% in 2020. And this is exactly how I'm going to show you how you are going to do that. So So Mitsubishi, you know, I told already, they talk about 15 and 20%. I talked about it. So the content of the talk. First thing we have to we can ask ourselves, does the Shockley-Queisser limit apply to organic solar cells? In other words, is there a fundamental reason why organic solar cells with ideal materials would be worse than inorganic? That's the first question. Second is, what is it? What is all this stuff about the charge transfer exciton? You heard about it today, and whether you believe it or not, we can just talk about it in a theoretical way and see what it does to the Shockley-Queisser limit, which is about ideal materials anyway, so it's a little bit funny information. And then we go to real materials, and then I'll show you how we calculated how you can do stuff better and what kind of efficiencies we can get. The first question is Shockley-Queisser limit applicable to OPV? And I don't want to go too much in detail. First, also, I have to admit that I am not really very good at Shockley-Queisser limit stuff. The physics is a little bit difficult for me, but it doesn't matter. Single band gap, detailed balance between absorption and emission, black body radiation, and that's the Shockley-Queisser limit for inorganic PV. You have under standard sun, you have an efficiency of 32–33%. OPV until now, what do we have? We have low dielectric constant, so therefore we have strongly bound excitations, excitons, and we need the donor acceptor heterojunction, and the absorption is mainly by the donor and or the acceptor, and only a very little bit usually you get an EQE from a CT state. There is people have done some good studies more recently, and you can see these things. Emission of the solar cell is mainly from the CT state. That is, but okay. Now here we go. What is the Shockley-Queisser limit? What the Shockley-Queisser limit is in such a way on ideal materials that have no dark recombination. All recombination is emissive. Only luminescent recombination. That, of course, that doesn't exist, but that's the Shockley-Queisser limit. These materials which only have luminescent recombination. So you would think, and this is the point for a real good solar cell. So a real good solar cell is a real good LED. For people who didn't know that. Yeah? So indeed, if you take a really efficient solar cell, but you put it in electrodes, and now you inject charges, you get an LED. Okay? And according to Shockley-Queisser, if you have the ideal materials, they should be really good because the only recombination is luminescence. Yeah? So if you put it as between two electrodes, you put charges in, according to Shockley-Queisser limit, all of them have to luminesce. Yeah? Okay, so it's very important. Okay, but however, when I talked about this the first time, what's his first name? Marcus Schauer. Marcus, at that time he was working on Tonarca, and they were screening a lot of polymers, and he says, well, what we see is if we have less CT emission, we have a higher efficiency. And what I just told you is that if you have emission really by the CT state, if that is your emissive channel, then a better organic solar cell should show more CT emission. And he said, we don't see that. We see the opposite. Oh, well, that's interesting. We have to look at it. Okay, now then it becomes a little bit more formal here. So we have a relationship between the external quantum efficiency and the electroluminescence. So we have a relationship between the action as a solar cell and the action as a light-emitting diode. So absorption and carrier collection, solar cell, versus injection and luminescence. Okay. So you can make this equation for the electroluminescence, and so that is that the luminescence you find is a combination of a product of the external quantum efficiency times the black body radiation spectrum, depending on your voltage. The electron luminescence spectrum is independent of the voltage within the relative relevant range. So as long as you are within the solar cell range, everything is constant. And we didn't find this, but this is what you can take from the literature. It's clear that the Shockley-Queisser limit is viable for OPV. If you have ideal molecules, there is no reason in the Shockley-Queisser analysis that it should be less efficient. So the point here is the Shockley-Queisser limit for OPV is 33% point, period. I'm not saying that we know how to make those materials, eh? That's a different story. Or how they would look, or whatever. So the next thing is, let's look at the CT state. So this is the analysis. How important is this CT absorption and emission for the maximum efficiency of an organic solar cell? In other words, is a CT state good or bad? Do we want a lot of CT state or emission and absorption, or do we want as little as possible? Okay, here we go. So we do a simple analysis. This is energy, and this is absorption. So, oops. Oh, diagram. Oh, is there another one? Break. This doesn't count. The middle one? Okay, yeah, okay. These are, the black line is absorption spectrum. And this is, of course, doesn't look like an absorption spectrum, but we do everything simplistic. So we said we have our main absorber in the solar cell active layer has this absorption. It absorbs everywhere in this area until the band gap. This is what it absorbs. And now we have an extra possibility that we have a CT state absorption. And the CT state absorption can be 0, or it can be all the way also 100%, let's say 1. So we can have this horizontal line is the spectrum of the CT absorption, and we will vary that between 0 and 1 with respect to the absorption of your active layer material. So this is the, this is the, this energy is E gap minus delta CT. So this is delta CT. Okay? This is delta CT, and this is alpha CT. This is the absorption. So this is the energy of the CT absorption, and this is the absorption strength of the charge transfer. What do we have in red? We have in red the electroluminescence, as you can calculate it, how the spectrum, the electroluminescence spectrum would be from an ideal materials combination donor acceptor with a CT emission. So this is Shockley-Queisser kind of materials, eh? Don't forget, they are really ideal. So as I just said, I gave you that formula, that's the electroluminescence formula, and you can put everything. This is again the quantum efficiency EQE at that wavelength, and this is the blackbody radiation. And because of the blackbody radiation spectrum, all your emission from your solar cell will be at the low energy side. That's because of blackbody, you multiply with the blackbody radiation. So this is the spectrum of emission from the solar cell. That is, it's a little bit funny, but that's because we have these block absorptions. So that's why all of this is sitting here. So in red is the emission, and in black is the absorption. And now we're going to do that would be nice. Oh, this is dead completely, of course. Ah, okay, I forgot that. The next step, so here in the middle you see, on top that's the spectrum, that's the plot I just showed you. And now what we do is we look at the efficiency, we look at the short circuit current density, and we look at the voltage of the solar cell. For a solar cell with an active material, active layer material with a band gap of 1.5 eV, and with a charge transfer state extra, delta, with this energy of 0.5 eV. Yeah? Okay, so let's say that means then that this is at 1 eV, and this is 1.5. Okay. So for that case, we can do the calculations. We can Jan Anton put everything in the computer, and of course here are some simple results. The first, of course, the open circuit voltage. If you go from a solar cell with this band gap to a solar cell with this band gap, of course your voltage goes down. So this is a logarithmic scale of the absorption of the CT state, going from very low, 10 to the minus 7, very low, to 1, which is then your solar cell has this absorption. Okay, so at 1, we have a solar cell with a band gap of 1, and then of course the voltage is going down to 0.75 or something, and it came from about 1. Shortly quasi, ideal, And then in blue we have the current. The current, if you have very little CT absorption, of course that doesn't really add to the action of the solar cell, but only if the absorption of the CT state really becomes interesting, then of course your current goes up, because now the CT state is going to help and produce current. So that's the blue line. Now we multiply blue by green and we get the red line. So what you see is the efficiency, the Shockley-Queisser limit efficiency of an organic solar cell with ideal materials. It is the Shockley-Queisser limit, roughly, it approaches that when you have very low CT state absorption. And then it goes down with the increasing CT absorption. And then at the end it goes up again. And then it reaches, of course, when it is 1, by definition, we have to be back at Shockley-Queisser limit. So it is exactly in accordance with what Markus Schaber saw, because Markus Schaber was here. Is seeing less and less and less and have better, or more and more CT, more and more CT and have a lower efficiency. You have to be here in order to get up again. He is in the wrong area. This is on a linear scale, and so this is the zero CT and all CT on a linear scale. It's very clear. We have to conclude that you want to either have 0 CT state, or the whole material has to be CT state. Now what does that mean? If the whole material is CT state, that means that all your donor and acceptor molecules have a ground state charge transfer interaction. So you don't have your original donor and acceptor, you have a new material. Only your analytical mind thinks of the 2 original materials, but that's wrong. You make a new material. Just like with 2 atomic orbitals, you make 1, or you make 2 molecular orbitals. They're different. So here is the same thing. If you have donor acceptor and you have full CT state, then you have a new material. And what does this new material mean? It means that it's basically one material. And if in one and the same material we make all these charges, you know what's going to happen. Massive recombination in reality. And so all CT state, I don't think, with the present materials is not a good idea. Maybe with later on. Okay, let me go fast now because it takes too much time. So I showed you this result for a material with an active layer band gap of 1.5 eV, where it's really dramatic. You can also look for active material with bigger band gap, and then of course then you get this green sheet. Depending on how the energy of the charge transfer state and the absorption of the transfer state, you can make all the calculations. I showed you the case for 1.5 and half an EV of this is the point that I showed you in my analysis, but you can do it of course for everything. I want to go and make the next step. Let's go to real materials. So we go away from Shockley-Queisser, we go away from ideal materials because it's very far away anyway, but it's nice to know that we have the same limits probably as inorganic materials. Let's go, now we go with a little analysis on real materials, and we're going to do 2 things that we want to analyze. We want to improve or look at optimization of kinetics. That's reorganization energy, mainly. And we are going to improve on the energetics. And I will go on the dielectric constant. Those are the 2 stories. Okay. You know that if you want to optimize the donor and the acceptor, you want to optimize these orbital energies. And what everybody has done until recently is this. You take a donor with the right spectrum for the solar cell, and you throw in this PCBM because it's a good acceptor. But you optimize everything here, and you live with the fact that you have PCBM, and then you optimize everything here, and you try to get this offset minimal, that you still have enough driving force for the forward electron transfer, and not that it is too big, because if it's too big, of course, you lose voltage. This is what everybody has been doing. And the first point that we want to make is that you could just as well work completely different. It doesn't help, but you know, as a start. And that is that you say, I have a perfect acceptor with a perfect band gap for the solar spectrum, and I take a donor, and I don't care about the donor too much, just like with the PCBM. I don't care about the absorption of the PCBM. I don't care about the absorption of the donor too much, but I optimize it totally for Hall transfer. So now the acceptor is doing all the action, and it is doing, this is 100% electron transfer solar cell, and this is 100% optimized, I must say, Hall transfer solar cell. And what do you think is a better idea? Well, there's no better idea. These are equally bad or good. What's a much better idea? To optimize both. Obvious, isn't it, when you think of it? It's stupid to have a colorless material or a useless material which only does accepting or donating, but no other action. It's much more efficient for a solar cell, weight, cost, if both materials do equal action. Obvious, I would say. So in that case, we end up with a very interesting situation where you must have two materials with probably quite similar band gaps. Not identical, I'm not saying that, we'll go into that, but they're probably quite close. Not 1 and 2 or something like that. Okay? So you optimize this, you optimize that, and then you have two materials. Now, if they have the same band gap, hey, remember, we're not talking about inorganic materials, we're talking about molecules. And molecules can have the same band gap and still show very complementary absorption. Because we have absorption spectra with molecules, we don't have blocks of absorption. Yeah? So I'll come to that, I'll show you. I'll show you that this has been done. This is exactly what people have been doing, maybe without noting it. So, first analysis is by Jean. And that uses classical Marcus theory, and Jean optimized everything in silico, that is, for charge transfer. So, this is the Marcus equation for the rate of the charge transfer. I'm not going to go into the details. What we do is the following. We look at the donor acceptor system, blue lines, HOMOs and LUMOs, and then we put in these dotted lines, and we put in the energy of the exciton. And you have an exciton binding energy, so we put the energy of the exciton here in the donor, and we put the energy of the exciton here in the acceptor. That you can do at will. You can put it wherever you like or you need it. And here, of course, we need it. We like it like this because now we can look at this difference. Delta G for the electron transfer is the delta LUMO, if you wish. And here we have the delta HOMO. That is the difference between the exciton in the acceptor and the HOMO level of the donor. Okay, that's delta HOMO. So, delta G for electron transfer is here, delta G for Hall transfer is here, and delta G for recombination is here. That's the effective band gap. Okay, everybody agrees? I hope. Okay, then Jean did all the gymnastics. You have to do quite some assumptions as well, because you have to put in some real numbers. So what Jean used is a device with a 7.4 efficiency. And maybe some of you know that that's not just something, let's say, how do you say that? Just somewhere out of the blue. That is this world record solar cell that was published a few years ago, and on which we know all the details. Some of the records that are 10% or higher, we don't know. We didn't know enough details to work with them. So we work with the materials that were known. That is PTB7 and 70 PCBM. Those were the two materials that we used in that 7.4 record solar cell. Sorry. And we use the numbers that are known, and we have to also assume a few things. In this case, we do not assume the CT state, by the way. And we also do not assume geometry recombination. And we assume a few other stuff. So this is a complex set of possible reaction pathways that can happen. Of course, now you have to start thinking, is this fast, Marcus, is this fast enough? Is it still good enough that it can work for the solar cell, or when does this go wrong? And here are the plots of the results. So, what we here have is the delta LUMO. That is this LUMO offset that I showed you, from the exciton level to the acceptor level. Yeah, that's the delta LUMO. And we can make the delta LUMO smaller and larger. If we are here, this dotted line is the real position for the real materials PTB7 and 70 PCM. There we have this offset, the offset delta LUMO is 0.7 eV. We take some optical densities, and we take exciton binding energy of 0.2 eV, and we take a reorganization energy for electron transfer, identical to the reorganization energy for hole transfer, that's 0.75. And then you get these plots. What does it mean? That if we would be able to put the donor levels a little bit different, we would still be able to optimize this solar cell a little bit further. And the final result is the efficiency is the red line. Here is the efficiency, that's the 7.4% efficiency as it was published. But if you could shift that polymer down a little bit more, you could reach 9%. That's basically everything that you could expect. And then that's all. Then it's fully optimized for this system. So how could you optimize the stuff further? Well, you know, we had, look at that, we had a reorganization energy of 0.75 eV in orange. You see it? And here we do this in silico with material that would have a lower reorganization energy of 0.3 eV. It's not crazy, but it's low. And now you see that the efficiency, if you go down, you can go down with you can have a smaller delta LUMO than in the previous plot, because we were surrounded here. Now we can go all the way here, and you can get to 12. What could we do more in order to improve this? Well, imagine, because our materials still are PCBM and PTB7, and they are not ideal with respect to band gaps. So if we would now make materials that is a kind of PTB7 with the same spectrum, I think. Isn't it shown? The spectrum is the same, but the band gap is just 1.4. Just shift the spectrum to 1.4. Okay, and then and we do that too for PCBM. And we have good mobility materials so that we can make a thick solar cell so that all the light is absorbed. And we have an EQE then of 0.9, and you have a low reorganization energy, and bingo, you get up to 20%. That's all you have to do. Okay, the next thing is that this computer is doing funny stuff again. Okay, sorry, same thing as yesterday, but we'll get there, don't worry. Okay, next step is dielectric constant. So what if we could do something about the dielectric constant? So here's a major point of the story. We have excitonic solar cells. We have excitons because we have a strong exciton binding energy. Why do we have a very strong binding energy? Because we have a very low dielectric constant. If you have silicon with a dielectric constant of 15, you can see in this plot that you see on the right that your binding exciton binding energy is in the order of kT. At least, let me say. So inorganic is the dotted line, and when they are in a distance of something like 10 nanometers, they don't see each other anymore. You have kT already. But in organic materials, and this is an organic material with a very high dielectric constant for your average organic material, namely 4, then you can see that you have a huge exciton binding energy. And this is, of course, something that you could try to work on. What would happen if we would be able to increase the dielectric constant of the materials? Here we go.
A higher dielectric constant reduces the exciton binding energy, as I just told you. You have Frankel excitons, they go with 1 over epsilon squared. You have a kind of an intermediate case, like with CTE states, where they say it's 1 over epsilon. At least that's what's in the Bible of this kind of physics. And then you have the 1A, and they go over 1 epsilon over epsilon squared again. So it's good for all kinds of excitons. A higher dielectric constant allows for a smaller LUMO and HOMO offset, because you don't have to overcome that binding energy anymore. Because the binding energy becomes smaller, and of course, also, if you have a higher dielectric constant, the difference between the triplet and the singlet exciton becomes smaller and smaller. So the danger of triplets, as you can hear that in optimized systems sometimes, would vanish. It reduces the Coulomb attraction within the charge transfer exciton. So the CT state is less bound. Not very surprising. It reduces Geminate recombination back to the CT state. Yeah? The dissociation probability at 0 field from the CT state becomes larger. A higher dielectric constant reduces bimolecular recombination. Recombination, a rate, there you see the formula, it is Langevin, and you see epsilon is there. It reduces trapecistal recombination. The capture coefficient is how do we say that? Inversely related to the dielectric constant. And finally, it reduces space charge effect. The upper limit for a photocurrent when the space charge limit is again linearly correlated to the dielectric constant. So these are all the things that I just told you. Yeah. So as the PhD student says, who works in this field, says the dielectric constant is good for everything. Very simple to remember. There is no single process in which an increased dielectric constant is a bad idea. So, here we go. Let's analyze that world record solar cell again. PTB 770 PCBM. At left, what you see is a spectrum, this is an absorption spectrum of that mixture. You see, first with open squares, the absorption spectrum of PTB7. You see that is a nice band gap with roughly about 20 nanometers. And then you see when you make the mix with 70 PCBM, that you see the 70 PCBM is what I call a complementary absorber. This is complementary absorbers. Same band gap, you see, same band gap. But PCBM does everything in the blue-green, and the polymer does everything in the yellow-red. Yeah, very nice. That's why people use 70 PCBM. Yeah. So, Jan Anton models that solar cell, and until he finds the nice fit with the real curve as it was published. So that's what you see here. The published one is the dots, and the line is the fit. That's for a 100 nanometer thick cell. And now we're going to play with this material. Now we're going to improve this material with dielectric constant K. Okay. First thing we do is we have some parameters that you have to put in, and here are all the parameters. We have to be honest, so we show all the parameters that we use. Well, maybe not for now, this is for reference. Okay, so the first thing Jan Anton did is say, okay, well, you know, they had to take a 100 nanometer thick cell because of the limitations by the material, mobility problems and so on. But if we now want to improve this, I want to have a nice thick cell. I want to have a 250 nanometer thick cell because then I absorb much better. Of course, the cell becomes worse. They the researchers had optimized the cell, and they came to 100 nanometers. So now if we go to 250, we should get a worse solar cell, obviously. And of course that comes out of the calculation. If you take a 250 nanometer thick cell, and you calculate, and this, oh by the way, the epsilon of 3 is roughly what it is what these materials are. Roughly 3. And if you now calculate the efficiency of the solar cell, with the 250 nanometers, yeah, but then of course it's not 7.4 anymore, it's 6.9 or something, because it's too thick. But now in silico we can say, okay, let's improve the dielectric constant of these materials, and we see this not so very exciting increase, but we get above 8%, and still not very exciting. Okay, so this is how you compensate for the increased recombination. Now we do the next step. The next step is the red point. The red point is that we take delta LUMO equal to the binding energy. That's the absolute minimum you can do. And it's 0.2 eV. So we go to the limit of what's possible, according also to what I just showed that Sean found using Marcus theory. So it is not crazy to go here. If you would optimize your materials, these existing materials, if they, as I just showed you with the Marcus result, if you optimize them with the HOMOs and the LUMOs, then you can get a higher efficiency. Exactly the same thing here comes from Jan Anton's result, and he gets, let's say, what most people right now tell you that is the maximum efficiency for a single band gap organic solar cell. And that is roughly 13%. You can find it in the literature. Some people will say 11, 12, 13, but that's about it. Which of course is incredibly sad if we have a world record of almost 11 and we're going to tell each other that we can never be above 13. I mean, that's the most demotivating thing that I could tell you as a teacher. Yeah. And it's not true. That's the good message. So, that's why I usually, if I give this talk, I say, I come and bring you good news. Okay, so 13. Here we are, 13. But that's 13 for materials that people will tell you that are getting materials. But what they forget is that they think that we will always have materials with a dielectric constant of 3. And that is the thing that you have to leave. You have to allow yourself the freedom to say, what would happen if we could increase the dielectric constant? If you increase the dielectric constant, I just taught you that the exciton binding energy goes down. I started here with a LUMO offset of 0.2 eV because the exciton binding energy at epsilon is 3 is 0.2. But if I increase the dielectric constant, my exciton binding energy goes down. That is this green curve. The green curve goes from 0.2 EV, as I said. This is the exciton binding energy, and it goes down. And you know that the exciton binding energy at 10 is about kT. Yeah? So we go from a strongly bound exciton to almost no binding energy. Already at 10. So what does that mean? Now what do I get? So I can decrease, according to this line, I can decrease the LUMO offset when I go to a higher dielectric constant. So, and I have the effect of the dielectric constant on all processes, and I get the effect on the LUMOs. And how does the curve look? Butts. This is how we say we can easily get above 20%. This is about 22%. So already at epsilon is 10, with kind of realistic materials. The only thing we do here is we increase the dielectric constant, and we know how to make these materials with optimized offset. And of course that is work, but it's only work. I hope you agree. We know quite well these days how to design molecules that have better offsets. I mean, you see it all the time. People are not crazy. You know, this is not so difficult anymore. So this, we can do this. Now the next thing is, of course, can we do this? Can we make materials, can we make molecules with a dielectric constant of 10? And if we are at 9, the exciton binding energy is kT. What does that mean? It means, ciao, bulk heterojunction, because you don't need it anymore. You have free charges. You have like silicon. We make molecular silicon if we would do this. So we come into a realm, if we come into a world, a material world that nobody knows. Isn't that really exciting? Because this is very good for solar cells, but not only for solar, this could be good for molecular electronics or organic electronics in general. It's a very interesting way, very interesting way. Okay, so we propose make the transition from classical organic and classical inorganic to molecular high dielectric constant semiconductors. So this is exactly what we promised in the project that I told you about on Wednesday night. I said we were working on this project with the new generation organic photovoltaics, exactly based on the whole idea of improving the dielectric constant. So that's the end of the story. I have 2 slides extra to make my story full circle on these 3 days. But first I want to conclude on this part. Shock quasar applies to OPV. When you have a CT absorption, you better have 0 or 100%, then you are back to the shock quasar limit. In the intermediate cases, it's not good for the efficiency. If you optimize the band offset, everything according to the analysis of Sean, you can get to above 20%. If you go to higher dielectric constant, that is, in our opinion, the key parameter for the next generation OPV materials. And because now comes something extra, we get bonus now. Now we get bonus. If you go to higher dielectric constant, that is most common that you would go to more like polar kind of structures that are water soluble. So we can make our stuff green. Yeah? But this means that you can go to a triple green technology. The triple green technology I was talking about. We make the procedures green, we make the chemicals in a green way, we make the solar cells green, with green energy, and you recycle. That's what we dream of. You guys have to do this because I'm too old. Okay, and don't disappoint me. With epsilon 8, you already can reach 26%. Well, I think that's too much. That's a little bit too optimistic, but that may be a low claim. Maybe it's 22. But anyway, with epsilon above 10, then the whole idea of that it is necessary to have a donor and acceptor and the whole show that we always talk about and all the problems that we have. Right? We have all these problems. And you know, we only have these problems because epsilon is 3. Yeah? So let's go away from that. That's the point. That was Sean. A clear vision for 2020. 20% for 2020, right? That's it. So these are the people that did that. I'm not going to go too much into that. I just want to be a little bit in front of you because I know that the question is, how do these materials look? The standard question is, yes, but how do you know, can we make those materials? And my answer is, yes, of course we can make these materials. Do I know exactly how to do that? I'm not going to tell you. Yeah? But we have to make it, of course, when we are doing that in Groningen, and, you know, you cannot talk about what you are doing today. I mean, that's a little bit too much. I'm not going to do that, right? But of course we are thinking, how do you get high dielectric constant? What does it mean for a chemist in the design of a molecule? Because dielectric constant is a materials property. A molecule does not have a dielectric constant. The material has a dielectric constant. Second, dielectric constant is a little bit more complicated than dielectric constant. There's this frequency stuff. Yeah, there's this frequency stuff. You have the dielectric constant at different frequencies. So how important is that? I'm not going to go into that. But the work looks good to us. But if you go and ask me as a chemist, how are you going to do higher dielectric constant? I say, very simple. As a chemist, polarizability, dipoles, polarity, and charges. Those are the things that you get, or that you use, that you see in materials, many high-K materials. And I'll show you one result. And now, here I come full circle with the whole story of the 3 days. What is a very polarizable material? No charges, no dipole, no heteroatoms, nothing, just polarizability. Voila! Here is the biggest atom in the world. Yeah, you know that for polarizability, people will tell you have to go down the periodic table because your atoms are bigger. An iodine atom is really, you know, like yeah? That's polarizability. Yeah? And so you understand that C60 is like a huge, those molecular orbitals, those are much bigger than iodine. Yeah? Those are really, really nice. And therefore, 4.5. It's completely apolar. There's nothing, it dissolves only in the apolar solvent, everything, although it dissolves very well in ODCB with high dipole. ODC, orthodichlorobenzene, very polar organic solvent. So anyway, so this is why C60 is such a good idea in the solar cell until now, because it enhances the dielectric constant of every polymer thus far. Yeah, in the, let's say the mean, the average dielectric constant is higher. And I think it's probably good for the next 10 years, because even if you now make a polymer with a dielectric constant of 10, then this 4.5 star is probably still not so bad. So I'm optimistic as a following chemist that I can still contribute a little bit. So this is now, I have shown you about 3 times all the processes that you have in an organic solar cell. And maybe other ones have shown it also 10 times to you. Those are the elementary processes in the solar cell. Well, that is only true with a low dielectric constant. And that's what everybody forgets to add. If you have dielectric constant, the low dielectric constant materials, yes, then you have excitron formation, excitron diffusion, interface, the whole story. But if you have higher dielectric constant, we can probably maybe put some stuff out, and we get from light absorption to charge transfer, independent charges immediately, and then to free. I don't know. Maybe I'm having question marks first, on purpose, because I also don't know, because nobody knows. But I think we have a lot more opportunities. And herewith, I come to the end. Thank you very much.
Questions?
Sorry, for your simulation, you fit in your parameter fixed, yes? For example, for the generation rate of the exciton, or generation rate of absorption, you think it as a constant rate? That means, for example, if you change the epsilon, the refractive index also will be changed. And with respect to the Maxwell equation, the distribution and the generation of the exciton is changed. That means we consider this one in the simulation for getting the high efficiency?
No, I don't
that
think
means
so.
you consider as
It
a
is,
constant?
I think
Because
so.
it should
Yeah,
be considered as...
I think so. I'm not sure. I didn't do this. Jan Anton Costa did this, and I just don't know the real answer, like, boom. I don't think he did that. But I'm not sure whether that makes a big difference if you use the whole, he puts it in the model which has all these recombination effects. Yeah? So maybe that's in a different way taking into account the same thing as you do when you use the Maxwell equations. But this is a little bit too difficult for me, I have to admit. So I pass. I don't want to tell you nonsense. Do you know that? Do you know the answer?
I don't know the short answer.
Yeah.
So, to make this material with the high dielectric constant is not so trivial, because you have other effects when you get charges inside, probably, and maybe if you put like very electronegative things there, you don't have the conjugation anymore, but the charges are more localized. I don't know. It's maybe not so easy.
Yeah, so you give bad examples.
Yeah.
Yeah, you already feel what you probably should not do. Yeah, I think I agree. But there are quite some options. We have to look into it. I mean, this is new, and this has to develop, and I hope it will develop within the next, let's say, a few years. But you see already, if you listen to Lupin Yu at the MRS conference I think that was this spring. Yeah, this spring he said, he had a little slide. He had a little slide. He said, I think my polymers are getting better, and I think I see some relationship with the dielectric constant. So he has good polymers that do what we like, and the dielectric constant has gone up. If you look at modern polymers, you will see more and more amide groups, polar groups. You see them coming here. Yeah? So it's not, and I think it's by accident maybe as it started, but now people they combine and say, So look at that. You'll get there.
Yeah.
I just wanted to comment. You see now in the literature, people are starting to do things like taking a polymer family and going to the blend and incorporate small concentrations of high K material and you see some enhancements. Do you think that type of approach will affect some of the processes that you talked about?
Yes. Yes. That's a known published way to enhance the dielectric constant of a material is to blend it with a very high dielectric constant material. Let's say nanoparticle kind of stuff. So this you can find in the literature. It's one way to try. Yeah? It's cheap, it's simple. You just buy it and you throw it in. But I am not so much in favor of enhancing, settling for enhancing just an average dielectric constant. I, as a material scientist, am way more interested in trying to make the real high dielectric constant semiconductors intrinsically. I think that's way more interesting. But of course, people do it, and we should try. Yeah, you should try. Yeah, sure. There's one way to go. Yeah.
Are there any other questions? If not, I think we should thank Kees for a really quite splendid talk.